Well, this is lecture 15 of the mechanical vibrations course. And what I have on the agenda today is this item, which is the discussion of the impulse response function. It sounds scary, and I think I should put it in perspective exactly what is it that we're after. Let me remind you that in the first 2 weeks of the course, we assume that in the vibration problem that we are looking at, there is no external force. And the result was that the mother of all equations, or the mathematical model which described that problem, was mx double dot plus cx dot plus kx equal to 0. For the past 3 weeks, we came and said, okay, what if the right-hand side is not 0? What if actually there is a force acting on this mass under consideration? Remember, we are looking at the single degree of freedom systems. In that case, the mother of all equations, of course, becomes mx double dot plus cx dot plus kx equal to f of t, whatever that force happens to be. But in the past 3 weeks, we assumed that that force had a very special form. For example, it was a harmonic force, which is F naught sine of omega t. F naught is the amplitude of the force, and omega is the driving frequency, or it could have been F naught cosine of omega t, which is the same story. These are actually very common in real life applications. For example, we discovered the motor imbalance leads to a harmonic load like that. But anyway, what we also want to be able to do to solve this mother of all equations with a non-zero right-hand side for an arbitrary function. In other words, I don't want to be restricted to harmonic force. I want to be able to solve it for any function that's given. In order to do that, we're going to look at a very special type of a function, which is called an impulse function. That is not obviously an arbitrary general function, but it paves the road to where we want to go. So that is the entire lecture today, which is dealing with impulse response function or impulse function. This actually is you have seen it in probably your second year dynamics class, but we'll review it a little bit. In fact, any force which has a value over an extremely small interval or over a short duration can be called an impulsive force. Okay, now, of course, we're going to make a little bit more machinery to do that. But generally speaking, if the load is applied over a very short duration, we can consider that to be, quote unquote, an impulse function. Now, in principle, the force that we are talking about, it goes from any time in the past, way in the past, minus infinity, to any time in future, way in the future, which is plus infinity. Okay, so the function f of t goes from minus infinity to plus infinity, but it's essentially alive over a very short duration. However, it still can be defined from minus infinity to infinity. It's just that it doesn't come to life except for a very short period. Now, some people call this thing shock loading, and obviously it is not a periodic function. I mean, basically it's nothing, and then suddenly something, and stays that, and then goes back to, for example, 0. Okay, so it is a non-periodic function. Now, if we assume if we assume that this is a very short duration where this function is alive, we will see that in fact all it does, because it's non-existent, it comes into life over a very short duration and then disappears again. We will see that something like that, if the force acts like that, all it does, it gives the mass an initial condition. Okay, we'll see that. So for the sake of illustration, let me assume that I have a function like this. Of course, it's if you look at this function, it starts at minus infinity, comes to t minus some value or tau minus some epsilon, and then it takes a value. This is a very special kind of an impulsive force that I'm talking about, and then it drops down after basically after another epsilon to 0, and then stays 0. See, the function essentially is defined from minus infinity to plus infinity, except that it's dead anywhere to the left of tau minus epsilon. Tau is this location, and anywhere to the right of tau plus epsilon. And the height of it is f hat, some number which we decide to call it f hat, divided by 2 epsilon. It's a very special kind of function. Nothing until this point takes the value of f hat over 2 epsilon and then drops down to 0 after the time tau plus epsilon. One thing is peculiar about this is that the area under this curve is this height. You can see that. This height times the width of this, which is 2 epsilon. So the area of this function that we have drawn here is f hat. It doesn't matter what epsilon is, okay? As long as, of course, epsilon is not 0, the area under this curve is f hat. So what we're interested, in fact, if it can be written analytically like that, okay? Anywhere up to t minus epsilon is 0. Anywhere after t plus epsilon, tau plus epsilon is 0. In between, it's just this constant function. Now, as I mentioned, the area under this curve, so the integral from minus infinity to plus infinity, which is the area under the curve, is the height times the width, which is f hat. And it's called, this thing is called a unit impulse, it's not the unit impulse function, the unit of this f hat, the unit of this impulse calculation. See that? This I, the I stands for impulse due to this force. The impulse due to this force is the integral of minus infinity to plus infinity f of t dt, which happens to be f hat. So whenever a function is given to us, we can always calculate the impulse due to it. And by definition, that impulse due to that function f is minus infinity to infinity integrated f of t dt. In this particular problem, the impulse associated with this very special function is simply f hat. You can see that. And of course, the unit of it, you can see that the unit of this is Newton second. Okay, so because it's Newton force times second. So obviously this f hat unit is Newton times second. What we are interested in is extremely short duration event, force. Now, of course, I can let epsilon equal to 0, or I can let epsilon go to 0, or at least think about it as epsilon approaching 0. So this I of f can be I of epsilon can be integrated for any epsilon, including the limit of it as epsilon goes 0. Okay. Now, when we look at this expression, we're going to see two properties. We're looking at the properties of the impulse impulse I as a function of f of t. This particular function, in other words, that rectangular pulse as epsilon goes to 0, we want to look at some particular properties. First of all, big F of t minus tau is 0 unless t is equal to tau. So, as long as t is not equal to tau. Okay. Already I drew that rectangle for you. You see that it's 0, 0, 0 until it reaches a particular area, then it jumps. Okay. So this function f, big F of t, in other words, the function that I drew for you, and the limit of it as epsilon goes to 0 has that property. And the other thing is that if I integrate that function, I get f hat. These are things that we discussed and they're obvious. Now, what I would like to think about is the limit of this function, the limit of this rectangular function. First of all, you can see as epsilon goes to 0, the height of the function goes all the way to infinity. Do you agree? Remember, the height of the function was actually f hat divided by 2 epsilon. As epsilon goes to 0, the function of it, the height of it goes to infinity. That function, this weird function, and it is a weird function because 0 everywhere, except at that one location. For example, location, which for simplicity, I took the centered at tau equal to 0, okay? This tau could have been anywhere. It's just that I took tau equal to 0 so that I can draw it like that. This weird function has no value or 0 value everywhere except at t equal to 0. And at that point, it shoots all the way to infinity. But the area under this fictitious function that you're developing, you're inventing something. The area under that is, in general, f hat, or for my particular interest, I'm assuming that f hat is 1. Okay? So here's the weird function that we have. It's 0 everywhere, except at one point. And that point, for simplicity, I'm drawing it at t equal to 0. At that point, it has a height infinity, but the area underneath it is 1. I'm assuming that the area underneath it is 1. In other words, I'm already thinking about f hat being equal to 1. That's a weird function. Don't let this thing fool you. The height of the function is not 1. It's the area underneath it that is 1. But it shoots to infinity, so how else can I write it? So what people do is this weird function. They call it delta function, delta of t, which is centered at tau equal to 0. You can see that centered at 0. If this was not centered at 0, it was centered at some other point, we'll draw it right there, okay? And the area underneath it's 1. By the way, this Dirac delta function, the reason it's called Dirac was a physicist / mathematician who lived until maybe 70 years ago. And he was a contemporary of Einstein and that gang. And he made a lot of contributions to this area. And that's why it's called Dirac delta function. All right. So I told you that Dirac delta function is the one that area underneath it is 1. Yeah, that's why f hat, if we go refer to the previous figure, is 1, okay? And the area underneath it is 1, and it shoots to infinity, and it's 0 everywhere else. Very strange. Okay. Now, in order to use this thing for the purposes that we have in mind, let us recall something from our dynamics class. There was something called conservation of momentum. You might say, what is all this doing with momentum? But just bear with me for a second. Conservation of momentum said that in the absence of any external forces, initial momentum equal to final momentum. Okay. And an example in the case, I'm looking at a bunch of billiards ball hitting each other, or bowling ball hitting a bunch of pins, etc., bowling pins, etc. Remember, this is true only if there is no external forces. So what happens when we take a hammer, mount it on a spring and a damper, and we hit the block, this block of mass M, with the hammer? Now, first of all, before the hammer hit the block, its position is 0 because it's sitting in equilibrium, just stays there, sitting there happy. And then there's no velocity. It's sitting there happy. So initial velocity and initial position are 0. This is before we hit it. Now, after we hit it, the change in momentum of this block will start moving, right? After we hit it with a hammer, it starts moving. And it's moved by velocity immediately when we hit it. It moves with a velocity x dot of 0. I put down plus here to remind you that this is after we hit it. Times the mass minus initial velocity times the mass. Okay, this is the change in momentum of the block. Change in the momentum of the block. This is the final momentum. Final momentum is as soon as we hit it. This is the initial momentum. Yes, I know this is 0 2. Yes, equal to mv naught. Okay, we write this thing as mv naught because this fellow, let me go back here. This fellow is 0 from up here, and m times x dot 0 plus, which means the velocity of the block at time 0. And that's why we call this thing mv naught. So notice that momentum before and after impact is not the same. Okay? In fact, we talked about the impulse momentum equation. In other words, this mv naught, which is the change in momentum of that block, is equal to the impulse due to the force that the hammer exerts on the block during that time, very short time. So this is the impulse to that force over a very short time, some magnitude. This is approximated with F times delta T. Remember, this is all integrated from minus infinity to plus infinity. I know that. Impulse is defined as minus infinity to infinity integrated F of t dt. But notice that this force is alive over a very short interval, delta T. So this thing is equal to that thing. And this is coming from the impulse momentum equation. So what is the conclusion? The velocity of the block immediately after the hammer hits it is equal to F delta T over M, right here. So if you told me approximately what was the time of the contact between the hammer and the block, the hammer does not stay on the block. It just hits it and goes away. Okay? If you gave me the T, and if you gave me an idea that during that short time, how much force is exerted, and I divide that by the mass of the block, I get the initial velocity of the block. Remember, I told you that if a force, impulsive force, acts on a body, essentially, the only effect that it has on the body, it gives it an initial velocity. And there we are. We can see that. In the context of this example, initial velocity is simply give me the magnitude of F, some indication of what it is, give me the duration of contact between the hammer and the block. I divide it by the mass of the block, and I give it the, that's going to be the initial velocity of the block. Okay? Let me read this thing. Hence, an impulse applied to a single degree of freedom mass spring damper system is the same as applying initial condition, zero displacement. Remember, this start at position 0, but the velocity is no longer 0. The initial velocity is just f hat over m, or f delta t over m. Okay? Okay, so let us go back to our mass spring damper system, and suppose we apply a force f of t, but not any force, an impulsive force. We just found out if this is an impulsive force, the only effect that it has in the block M is to give it an initial velocity v naught. Okay? Remember, I said that if you give me the value f hat, which is an indication of the force is, what the force is during that extremely short period of time, I can multiply that magnitude by the delta t, by the time duration, and divide it by the mass of the block, and that'll give me the initial velocity of the block. Okay, so because it's an impulsive force, f of t is 0, except that it leads, that impulsive force leads to an initial velocity, which happens to be f hat over m. We are assuming that the initial position is 0. So when you take the mother of all equation, the right-hand side is 0, except for that extremely short duration, which is in fact the result of initial velocity, but not f of t. Okay. So if you divide both sides by m, you're going to get this classical equation that we are used to, and the right-hand side is 0. The only thing is that x has an initial velocity, or the mass has an initial velocity, therefore there is an x dot 0, which is called v naught, and of course initial position is 0, x naught is 0. Okay, now let me remind you that we spent about a week on solving equations like this. In other words, the equation where the right-hand side is 0 and subject to given initial position, initial velocity. Yes, of course, initial position is 0, I understand that, but initial velocity is not, and we found the solution to this equation, and it came out to be this horrible expression. Okay? Assuming that there is oscillation or underdamped situation. Now notice that here, we have an x naught. Of course, this x naught will be 0. Okay. We have a v naught, and that v naught will be f hat over m. So we can rewrite this thing based on what I just said, namely x naught equal to 0 and v naught equal to f hat over m, and we come up with our solution. Now, let me also remind you that when we discuss these things, the magnitude of the phase angle in this problem came out to be that expression. Okay, or just this is all review from about 5 weeks ago. Okay, now let's go and plug in our known values. Initial velocity is f naught over m. Initial position is 0, and let's see where it takes us. Well, that ugly expression on the previous slide comes out to be this. All right? And let me remind you what this f hat was. This f hat was the impulse due to that impulsive force. In other words, this f hat, I want to remind you that it was actually the integral minus infinity to infinity of that impulsive force f of t dt. Okay? So notice that I can rewrite this expression as f hat times times these three terms. So I can write x of t as f hat times something, a function. That function is just this combination that you see there. Okay? This is such an important function, and it's called response due to a unit impulse. Now, where is that unit stuff coming from? Notice that in general, if you have an impulse of size f hat, in other words, if the integral from minus infinity to infinity f of t dt came out to be f hat, the solution to our problem, in other words, the displacement of the mass is right here. And therefore, if f hat just happens to be 1, then of course it simplifies to h of t. X of t is going to be h of t. So this solution, response of the system in terms of the impulse function, this is called impulse function. This h of t is called an impulse function, and sometimes they say unit impulse function because there is a value 1 here, because it would have been the response if f hat was unity, f hat was 1. Okay? So this is the response due to a unit impulse function. And that's a fancy way of saying that f hat is 1. Okay? Now let me remind you, the unit impulse function is our delta t. Delta t is a unit impulse function because it's 0 everywhere. At the place that it acts, it goes to infinity, and the integral of it, which means the impulse of that function, is 1. Okay? So h of t is the response due to the unit impulse function delta tau. At tau equal to 0, of course. And this is also called Dirac function, Dirac delta function. Okay? Now, based on what we know from, elementary, if you want, math, if this happens to be, well, I say elementary math, I mean calculus, for example, if this impulse function was not centered at tau equal to 0, but it was centered somewhere else, essentially nothing happens to h of t, nothing happens, there is no response until the time t equal to tau is reached. And at that point, there's a solution, except that there's a shift in t because nothing happens until t equal to tau is reached. So another way of looking at this is saying that, okay, h of t minus tau is the unit impulse response because of the delta function acting at tau at time t equal to tau. The solution to this is right there. The solution to this is the same expression, except that t is replaced with t minus tau. Just think about it, and it makes sense. Because this essentially is what is causing the displacement, okay, what is causing the block to move. If this happens at time tau, nothing will happen until the time tau, and then after that, it will move just as if it happened at that instant. Okay, one more time. This is the unit impulse response, or simply impulse response due to the delta function at time tau equal to 0. This is the impulse response due to an impulse which came to living at time t equal to tau. T is shifted by tau, t minus tau. Okay? These are both called impulse response function, and some books call it unit impulse response function because the f hat value that ordinarily is sitting here is 1. Okay? Now I want to make some remarks about this impulse response function, h of t. First of all, it represents, although remember, this h of t came from delta function, Dirac delta function. And Dirac delta function is a function that's 0 everywhere except at the place where it's centered, which goes to infinity, obviously, and the area underneath it is 1. So it's a mathematical tool, basically. However, it's an excellent model for a force that applies during a very short period of time. This represents the response due to a force that is 0 everywhere except t equal to 0, shoots to infinity, that force shoots to infinity. However, the area underneath it, if you can visualize it, is 1. Okay? Not a true function, actually. You can see that. But it's an excellent model for a force over a short period of time. Okay. Now, so one more way of saying it is that impulse response, this is the impulse response, is physically interpreted as the response to an initial velocity and no initial displacement. This is what we had in the previous slides, okay? So h of t is the response due to an initial velocity and 0 initial condition. That's it. Now, later on, we're going to see how this h of t is going to help us to solve the problem with the mother of all equation, the right-hand side of it being an arbitrary function. This is yet to be seen. It is by no means obvious how this is going to take us to where we want to go. All right? A very good example of when we have impulse function is an impact. For example, the hammer, it hits the block, it doesn't stick to it, it hits the block and let it go. Notice that when it hits the block, it stays in contact with the block for a short duration of time, right? So it is not like a delta function where that width of time is 0. And it doesn't go to infinity either. Okay. However, if you integrate that function, whatever it happens to be, over that short period of time, which means actually from minus infinity to plus infinity, because it's not in the picture before the time that it did it, and it's not in picture after it left it. That integral is going to be the impulse due to that hammer f of t. Okay. Now, in testing devices, people use actually a hammer, impulse hammer, and that actually records for you the duration of the time and the magnitude of the force that's magnitude of the force that is imposed on the thing that we are hitting it with. Now, of course, it's not going to be constant. It's not going to go to infinity either. However, it'll give you the value of basically impulse that is applied. Okay. Now, something has to be. We have to be very careful about this business of a force acting over a short duration of time. What does that mean? What is short? Okay. Now, for now, let me say that when we say delta t is short, compared to this number, now remember, this number is the period of oscillation of the undamped system. Okay, so if we have our mass, if we have the spring, we have the big T, we have omega n, big T. So this delta T must be small compared to that number. But that statement by itself is also a loaded question. In other words, in many literature, you see that, oh, it says the vibration test or these tests that we do, these hammer tests that we do are of order of milliseconds. Okay, milliseconds. So yeah, millisecond, but in principle, it should be small compared to this, because what if this hypothetically is a microseconds? Is millisecond small compared to a microsecond? The answer is no. So you have to be careful, okay, in view of some of the statements that you read, because is this small? Not compared to 10 to the minus 6, not compared to 10 to the minus 2. Yeah, compared to the 10 minus 2 is small, or compares to 10 to the minus 1 is small compared to that. But in reality, this delta t, when we say small, it's comparing it with the natural period of vibration. Okay. Okay, so let's do an example where these things are actually used. Very often in instrumentation, or experimentation, we use an instrument hammer to excite a device. Okay, and this is basically to hit it with the hammer, and the hammer will excite it, of course, and it also electronically measures the impact force and the duration. Okay, so let's look at a case, for example, if a device is tested, which is a single degree of freedom system, so it's basically a mass spring damper, which we are hitting it with a hammer, and the hammer records an impulse of 0.2 Newton second. So this comes from the instrumented hammer, and these are the characteristics of the mass, damper, and spring. Okay. Now, it also happens that when you do these experiments, sometimes either on purpose or inadvertently, a second hit is recorded or actually implemented. So this is called a double hit. Double hit takes place, and the solution then is going to be, of course, the initial hit, which was 0.2. There is 0.2 delta t, and then a double hit, the second hit, which is 0.1. This is the impulse value times delta t minus tau, and tau happens to be a little bit later. Okay. So what we want to do is to find out what is the response of that mass spring damper system to a loading which looks like that, impulsive loading. This is the first hit. This is the second hit. And notice that the difference is these values are different, of course. And of course, this takes place, let's say 0.5 seconds later, half a second later. Okay. So here is an example of the type of impulse that we applied. This is the initial one with a height of 0.2. I mean, remember, when I draw a rectangle, this is an idealization that we're going to replace it with a delta function, 0.2 delta at t equal to 0, or 0.2 delta of t minus 0. Okay. And a second hit, a double hit, is going to be 0.1 times delta of t minus 0.5. Okay? So here is an example of an instrument hammer where the guy is hitting, a device and trying to record the data and excite that device. So let's start with the first hit. In the first hit, this is what you've got. Okay, so we have an impulse of 0.2. That means this area is 0.2. And we can write the response. We can write the response of the device by taking your f hat, whatever it is, multiplied by h of t. Remember the things that we did a few minutes ago? Okay. In order to do that, remember h of t itself involves omega n, zeta, omega d, and the mass of the device. So here's omega n, root of k over m. Zeta, c over c critical. We are given the value of c of the single degree of freedom system. And because we have the mass and stiffness, we can calculate the damping ratio. And then we can find damping frequency, which comes from this. And now we can write our response. So it's going to be f hat h of t, or f hat, here is h of t, the whole thing. We replace the values, 0.2 for f hat. This came from the instrument hammer. We put the mass, 1 kilogram, omega d, we just calculated it here. E to the minus, there is your zeta. There is your omega n. Of course, there's a t. Here is omega d times t. So we got it. There it is. And in fact, until the second hit occurs, the double hit occurs, this is the response of that device. For example, if you're thinking about mass spring damper system, here's the displacement of that mass. Now, when the second hit occurs after 0.5 seconds, we know the value of f hat is 0.1, also coming from instrument hammer. Okay, so we just write the solution due to the second hit, with this data, f hat 0.1. So we write down basically 0.1 times h of t minus tau, and tau is 0.5. There we are. F hat h of t minus tau. Remember the expression for h we have? Every time you see a t, replace the t minus tau and just clean it up right there. Yes, you multiply these things. Remember, this f hat is 0.1, is the second impulse, and this is the cleaned up version. So after 0.5 seconds, the first solution exists, the first response exists, but this is also created. So before 0.5 second is x1. After 0.5 second, it's x1 plus x2, because both of these responses are, and you add them up right there. So less than 0.5, what we got initially, previous slide. After 0.5, whatever is up there, plus the new one that we got. Now, I'm going to plot this. Look at what happened. This black curve, is the initial response, first hit. However, we know that at 0.5 second, that is no longer valid. Up to 0.5 second, there is a black curve. After 0.5 second, it's the sum of these two that plays a role. So if you add these two up and plot it, we get this. This black one after 0.5 second is totally irrelevant. What is important is the sum of these two after 0.5 second, and that's what you're seeing here. Yeah, so solid line is response of the first hit, initial hit. and the dashed one is the sum of the two. Okay. And notice that when the second hit occurred, it gave it a bigger initial velocity. That's why this slope, which represents the velocity at the time, at any time, is now higher because a second impulse took place and that added to the velocity of what was going on. Now, here's a problem which is very similar, except that there's two points that are different. First of all, the right-hand side, notice that before we had, for example, we had 0.2 times delta t plus 0.1 delta t minus 0.5. Well, first of all, for simplicity, instead of 0.2 and 0.1, we have 1 and 1. But there's a minus sign here. And there's one more thing. We are told that this system initially, in other words, even when it was being hit by that impulse, it had a position, initial position, and an initial velocity, which means we have to do a little bit more. Remember, we're going to do this thing twice. First of all, we're going to ignore, we pretend that this is all before 4 seconds. In other words, the second piece is not even here. The double hit is not even here. What we have is x double dot plus 2x dot plus 4x equal to delta of t. Never mind about that, because we are below 4 seconds. And there is an initial velocity, an initial position for the block. First, we ignore this. Let's ignore this initial position, initial velocity. Let's just concentrate on left side equal to delta t. Okay? Well, we know what the solution is. The solution is 1, or your f hat, times h of t. Okay, so we have to find h hat. We have to find h of t. Okay? What do we need? What do we need for h of t? There is omega n, there is zeta, there is omega d, and of course the mass. Now, because of information is given to us like that, we know what m is. M is 1, and we know what omega n squared is right here. Okay, this is omega n squared. This plus 2 is 2 zeta omega n, right? And omega n, we get it, and zeta we get. Out of that, we get omega d, which is square root of 3. Now that we have this information, we can write our ht. Pretend, remember, we're ignoring this stuff, this red stuff here, initial position, initial velocity. So we just write down the expression. Here's the expression for h of t. Your f hat is the coefficient in front of delta. That's 1. Everything else we calculated. And we're going to get this. Now, this is the solution due to the impulse. But the assumption when we do the impulse, remember, if you go back half an hour ago, 45 minutes ago, the assumption was initial position was 0. Okay? Now here, we have initial conditions. So it's going to be this plus the stuff coming that is responsible for these two. And that is the second week of classes. We did it right there. So the homogeneous part, well, delta on the right-hand side, just 0. With initial conditions, they're buried in A and phi. And you just have to go and either directly plug it in this expression or look at the formulas that we developed back then. This is the second week of classes for what A and phi are. Let's do that. Here is the response due to the impulse. That's fine. This is the response due to the initial conditions that we have to find A and phi from. You can do it directly, as I said, or you can go and find out how A and phi were related to X naught and V naught. Okay, whatever is convenient for you. So I'm just going to use this thing directly. Okay, and if you do that, you just plug in the expression for in this expression for x of t, the whole thing, right? This solution is right here. Don't just take the first part, because remember, the second part must be there. I just caution you that when I said go back to the stuff that we did from several weeks ago, second week of classes, uh, there was no second part. So in a sense, those formulas by themselves do not directly apply to a present situation because we have the leftover term here, right there. We have the leftover term here, okay? There. So this is probably the easiest way of doing it. Again, I want to make sure that you realize that do not go and find out how A and phi were calculated without second term being present. Okay, we talked about this thing when we did harmonic problems also. Remember when we did the harmonic response, we didn't just go ahead and use the same formulas for A and phi, because the piece that was required for a particular solution had to be included, or for one had to be included. Okay, let me not dwell on that thing. If you're interested, you go and check it again. So when t is 0, notice that that'll give you this combination, will give you a sine of phi equal to 0, and you differentiate this thing and you set t equal to 0, and you're going to get the value. Another equation involving a and phi. You just literally have to differentiate this thing and then plug in t equal to 0 this, and you have to solve for a and phi somehow. And when you do that, it's very easy. You find A out of this, plug it in the second one, or let me put it this way. A sine of phi is 1. So notice that we're going to get A square root of 3 cosine of phi. Let me see that. See, this thing from the line above it is 1. So minus 1. And you're going to get, let me put it a different way. If you find A out of this, if you find A out of that, you're going to get 1 over sine of phi, right? You plug it in here, you're going to get tangent of phi equal to something, and that'll give you the value of phi, okay? So the problem is that if you just replace this thing with 1, that's fine, but then we also have A here, okay? So all I'm saying is that maybe it's better if you find A out of this, plug it in there, and plug it in there, and solve for tangent of phi, and you know what the value of phi is. The only thing is that we know that phi has to be between 0 and pi. So that's why don't take this value, add pi to it, and you get 2 pi over 3. Once you have phi, you have A. There we are. And we know exactly what the solution or what the response of the device is, the mass is, when t is less than 4. It's going to be this plus that. That came from the impulse, unit impulse. That came from initial condition. Okay? So when you plug it in, this is what you get. Now, after 4 seconds or at 4 seconds, you're told that impulse of -1 is imparted to the block. Now remember, this -1 essentially means, because it's minus, it means that you're trying to actually stop that block. So you hit it from the other side. Okay, you hit it from the other side. Okay, now, because this is happening at 4 seconds, to write the answer, the response due to this impulse, you just put the impulse there, f hat, which is minus 1, and h of t minus tau, where the shift or tau is 4. So just plug it in, clean it up, and you get this, okay? So before 4 seconds, right up here. After 4 seconds is this thing that we got plus that. Before 4 seconds, what I said, after 4 seconds is the sum of these two. And when you plot it, you see that this red one is the first line of this expression. In other words, it's the response before 4 seconds due to that impulse that we gave it, initial impulse that we gave it, and initial velocity that the block had somehow. Okay, it's this red one. After 4 seconds, we give it a hit, double hit, with a minus sign. That means actually the direction is reversed. So when you plot this fellow, you're going to get the blue one. So the overall response is the red or the dash up to this point. And after this point, this red stuff is nonsense. It's just the blue one. Okay. All right. The sharp change in the response is is because we are applying a second hit, and this is in contrast and in the other direction with a negative value, right? This is in contrast where we did the first previous example where it was 0.2 delta plus 0.1 delta. Here we have delta or 1 delta minus 1 delta, t minus 4. That's why it's going down. All right. We have another example here. We have a bullet that's coming in at with a mass of m naught, and it's coming with velocity v, and it's going to get embedded in that mass that is attached to the wall with the spring and a damper. Now, obviously, this thing begins to vibrate. This thing begins to vibrate, and we want to know the natural frequency of vibration of this mass. Now, first of all, you have to realize that in this problem, there is no external force. When the mass comes in with this velocity and gets embedded in this thing, yes, there is interaction between the mass and the interaction between the m naught, the bullet, and this mass, but it's internal because whatever force is exerted on m naught once it gets embedded, it's also exerted on the mass itself, the big M itself. And you might say, what about these reaction forces? Well, these reaction forces, okay, at that instant are not external. Okay. Yeah. Because so this is basically a conservation of momentum problem. Okay, momentum is conserved during the time that initially this gets embedded and vibration begins to take place. Okay, there is no external force. And that will give me the initial velocity of the block. We know the initial velocity of the bullet, but we don't know the initial velocity of the block. Okay. I also want to remind you, by the way, that the forces due to the spring and the damper, that initial hit, there is no time for them to produce an impulse. Okay, remember these were called non-impulsive forces. Okay, back to dynamics. Spring force and the damper force are non impulsive forces, or as a matter of fact, gravity, non-impulsive forces. This is why we are saying that there is no force which gives you an impulse. Yes, as I said, the bullet embedded there is force interaction between them, but those are internal. They're not external. Okay? And therefore, out of that, we calculate the velocity of the block. Okay? And obviously, this is the mother of all equations. All right? And out of that, we get the natural frequency. All right? Why did obviously this is the information that we need in order to solve the problem. The natural frequency, notice that is uh, it has nothing to do with this x dot zero. It has nothing to do with that. It's just that once this gets embedded here, the total mass of the object is m, big M plus little m naught, and the stiffness is k. So this piece has nothing to do with what we did on this side. Okay, all right. The problem involves impact. Develop the mathematical model to represent the vibration. So basically what it's saying is, tell me what the initial velocity is, initial velocity of the block, and then find the natural frequency. These are independent items. Another problem that we have is a package dropped from a height m. Assume that the package, it hits the ground and doesn't bounce, it just sticks to the ground. We want to write the model of the vibration problem and find out why is it that we'll find out that this mass m, an impulse imparted on it. Okay, you see, when it hits the ground, an impulse is imparted to the mass. Okay, now it's not obvious what this is. There is an impulse imparted to the mass at the time of contact, okay? But it's not obvious what that thing is, okay? And as part of this, it says find the maximum acceleration of the mass, okay? But we'll do that later on. First of all, if you have the gadget like that, it's dropped from the height h, it reaches the ground, and he reaches it with the velocity that we know where it is. So we convert basically potential energy, which is mgh, to kinetic energy 1/2 mv squared. Okay, this is the standard thing that you do in your dynamics class. Initial velocity is 0, so we have 1/2 mv squared equal to the work, the potential energy, or work done by potential energy, which is going down, of course, positive, and you're going to get the velocity when it hits the ground. Okay. All right, so we have the velocity of this gadget when it hits the ground. So the mother of all equation, it sticks to it. Okay, mother of all equation, there is no more force, no external force acting on it. Initial position is 0 before it starts to vibrate, and initial velocity we just found. Okay, now we found the solution to this equation. Let me go back here, right there. We found the solution to this equation. Initial velocity, initial position, which happens to be 0, and the mother of all equation. We found the solution. It came out to be like that. So can we just plug it in? Okay. This is from slide 11 of lecture 3, third lecture, basically. So if you just plug in based on the information that we have, we know V naught, which is root of 2gh, plug it in, you get phi equal to 0. There's the solution. If this is the solution, you can see that it's just like my impulse response function. just like my impulse response function, except that it's not a 1 here. It is the root of 2gh. So this must be the impulse imparted to the mass at the time of contact. That value, square root of 2gh. And then it says find the maximum acceleration. But of course, to find the maximum acceleration, you know how to do this. You differentiate this thing, for example, twice, okay, and set it equal to 0. Actually, if you want to find the maximum acceleration, the maximum x double dot, look, the maximum x double dot, to find the maximum something, you have to find its derivative, right? You have to find its derivative. So you have to find the third derivative of this expression, and then set it equal to 0, and then get the time, and take the time and plug it back in. This is ridiculous. So instead, if you have this information, we can actually plot the second derivative. Okay, now we're going to do a problem that's a bit more realistic. Take an airplane wing that is modeled as a cantilever beam, and we're assuming that the mass of the wing is very small compared to the mass of the missile that is it's firing. The modulus Young's modulus of the beam is given by E. Let's assume that it's made out of a material which has E as its Young's modulus and I as its cross-sectional moment of inertia. Now, keep in mind that this is an oversimplification, but this is a first attempt to model the wing in a very simple way. So we're going to assume that the beam is the wing is a beam like that with a constant mass constant moment of inertia and Young's modulus E. That means that we know the stiffness of this beam from strength of material. We know that the beam under bending has a stiffness Ci over L cubed. L is the length of the beam as indicated here. Okay. Now, let's assume that when the missile is fired, it puts an impulsive load on the wing of the type F delta T. Now remember, this means that it's impulsive force. It's not there before it's fired. It's not there after it's fired, and during a very short duration of time, in the limit 0 time, basically, it puts an impulse of F magnitude F on the wing. Okay. Some information is given here about the values of these things. For example, this is for aluminum, length of the wing 4 meters, damping ratio, we're assuming damping ratio of 0.01, and the mass of the missile and the carriage missile carrier system is 1,000 kilogram. Okay. Now, keep in mind that by writing that, we are assuming that it's an impulsive force, and let's say that the magnitude of that impulsive force is 1,000 newtons, and the firing lasts 0.02 seconds, maybe 20 milliseconds. All right. So we know what the response of the single degree of freedom system is going to be under an impulsive load. Now, in reality, this F of T, the force that the missile puts on the wing, is not constant. Okay, now it's some jagged force, but it's very, very short duration. And what we have done here, we said, okay, if we calculated this area, if we had our hands on this weird looking function, and if we calculate this area over this, over this time duration, we get some value. Okay, so let's take an average value. Average, pretend that this is not actually varying with time in this weird way, but in some average value, or it has average value of 1,000 newtons. So that means that the impulse is 1,000 newton, okay, multiplied by 0.02. Okay. The actual plot of F versus T is kind of jagged and it's kind of erratic. However, if we take an average value so that it has the same area underneath as the area of the actual experimental curve, then we can use it for what we have in mind. Let's plug in the different values that we have for the information provided, the stiffness of the spring, the natural frequency of the spring, K over M. We are assuming that the wing is massless compared to the missile and the missile carriage system. So here is the omega n. We need the damping natural frequency. Okay, and then there it is. This is the response of the beam from zero initial condition, zero initial position, and the velocity imposed by this impulsive force. Okay, so there we are. This is the stuff that we did in the present lecture. So we can just plug in these values here. F hat, okay, F hat divided by M omega D is going to give you this number, and it's obviously it's a decaying solution, and there is sine damping frequencies here and times 2. Okay, now we can plot this, the response of the function, the position of the tip of the wing basically as a function of time. It's a decaying solution. If you look at only a very short period of time, which actually, you can see it's oscillating, but the amplitude is decreasing, as you can see here. Our final example is something like that. We have a structure made out of steel, and the force F acts at time t equal to 0 like that, and it has a magnitude of 1,000 newton for a very short period of time. So it's alive only for that duration of time with that kind of an average value. Okay. Now, what we want to know is the angular deflection of the disk after 1 second. Okay. So what we want to know is, where is the disk after 1 second? Now remember, if this f of t was harmonic, sinusoidal, then we spent 3 weeks on that. But this is not sinusoidal. It's an impulsive force. And later on, we're going to solve it when f of t is not impulsive, but it's an arbitrary general description. That's going to come in the next lecture. But for now, it's an impulsive force. Okay? Now, some information is given here. This is made out of steel, Poisson ratio, Young's modulus, and the impulse due to the moment is going to be the magnitude that's given here, 1,000 newton, times the moment arm, which is half of this diameter. So 0.25 over 2 is this radius where the force is acting to the center. So this is the moment arm, basically, 10,000 newton times the moment arm times the duration, and this is going to give you the impulse due to this moment, and the unit, of course, is Newton meter second. This meter is because we're taking moment. Okay. Now the rest is history, because if this was F hat, that was the solution. Well, it's M hat, okay? M hat, and we are ignoring damping. If you're ignoring damping, this M omega D becomes omega n. And of course, because it's a torsional problem, we're not involved with the mass. We have J here. That's the polar moment of inertia of this disk, about its center, plays the role of the mass. and then all the omega d's are omega n because there's no damping and there's no exponential. Now, in principle, I have to calculate J, and let me remind you that J is 1/2 mr squared, 1/2 mass of this disk, 1/2 mass of this disk times the radius squared. We also need the value of omega n, of course. Now, omega n, because this is a torsional motion, torsional mechanism device, omega n is going to be root of k over j, not k over m, k over j. So all of these have to be calculated. How do we find j? J is the polar moment about the axis. So basically we have a fancy torsional spring here. See that? This is our spring. This plays the role of a spring. And we have a formula for the stiffness of the spring, this fancy spring. Okay? So this is coming from slide 15, lecture 4, Gj over L. Okay? So G is the shear modulus of that shaft, and L is the length of that shaft, and Jp is pi d to the 4 over 32. Okay? So if you know the diameter of this, you can calculate Jp. And if you know Jp and G and L, you can calculate the stiffness of this torsional spring. Okay, so I'm going to put this thing on a MathCAD worksheet. This is what I told you already, square root of k over j, but k is this weird thing. This comes from lecture 4. So I put the stuff in MathCAD worksheet. The diameter of this shaft is 0.04. The length of this rod is 0.6. The radius of this disk is 0.25, and the height of the disk right here is 0.1. Density is given, Young's modulus, Poisson ratio, shear modulus. Yeah. And I told you in one of the earlier lectures, I wrote something on the board that G was E over, I think I misplaced the 2. The 2 is in front of this parentheses, okay? Right. So F is 1,000, force is 1,000, duration is that, and the impulse is going to be this force times the radius, which is going to give you the moment, impulsive moment, times delta t is going to give you the value of m hat, which is impulse. Now let's find the mass of the disk. The mass of the disk is pi times the radius of the disk squared times the height of the disk times the density. Okay, and this is the mass of the disk, and J of this disk is 1/2 m of the disk, radius of this disk squared. So m of the disk is right there, based on the numbers that you got. And 1/2 of this m times this radius, which is incidentally 0.25 divided by 2 squared. Okay. So we calculate Jp. Jp is for that shaft, that fancy spring, pi diameter to the 4 over 32. Remember, diameter of that shaft was 0.04, and the torsional stiffness of that fancy spring is right here. Okay. Find the natural frequency now. K torsional over J. Usually it's K over M, but this is a torsional system, so it's square root of K over J, and this comes out to be 327 Rad per second. And then we just stick it into the formula for H of t. This is the unit impulse due to this is the unit impulse response due to the unit impulse. Ordinarily, if we have an m hat here, that's going to be the response itself. But we do have an m hat. M hat is right there. So we just take that, whatever this value is, and multiply it by this fellow, and this is going to be the response of that disk. And that's it. You want to know how many degrees after 1 second? Just plug it in. T equal to 1. You know everything, and you get 0.027 radians. It has to be converted to degrees, approximately 1.57 degrees. And that takes care of the lecture today. Here's the plot of it, by the way. No damping, the amplitudes stay constant.